Today we are going to discuss a very important device, transistor. As you know that transistors are very important, they are used in both analog and digital circuits. They can be used for, and they are used for basically for two functions, as a amplifier and as a switch. So, if we look at this very important device, let us first try to understand what kind of electronic device we are trying to generate. So, if you before we get into the details of how this device is made and how we get the characteristics from a semiconducting device, transistor characteristics from that, let us just spend some time to understand the applications or what kind of characteristics we want in a transistor. So, if we have a device, for example, in a circuit which is a two terminal device, and I apply voltage across this, then normally I am expecting a IV characteristics from this two terminal device, which I am going to call it make any arbitrary shape maybe of this nature. And so, depending on what is the voltage that I will apply, I will get a current, and I have no other control on this particular device. Now, if I change this device into a three terminal device, and transistor is a three terminal device, and I am going to provide a control. So, this is a transistor, and I am going to provide a control through a third terminal to this transistor. This control could either be a current or it could be a voltage, and I am trying to see if I can change different type of device curves in this case. So, now I have a device in which I have provided a third terminal to my transistor, and this third terminal current or voltage applied has the capability of changing the output of the device. So, this would be the third terminal current, it could either be a voltage also, one value at a different value, it will have a different IV characteristics and a third value. So, this is the importance of a three terminal device, where the third terminal signal is being used to control the IV characteristics of the device. Now, how is it used as an amplifier or a switch? To understand that, let us put a load in this circuit. If I put a load on this circuit and I want to see how the circuit operates across this load, then I need to, in order to find the operating condition, I should make the load line, which is going to be like this. This would be the value if for the resistor that I have put here, for the load resistor. This is when there is no current flowing, and this is the value for the current in the maximum value for the current in the resistor, and this particular device then will operate at this point and at this voltage and current. Now, for a two terminal device, you have only one operating position for the load in this particular case, but if I have the same load in with a three terminal device, then I have possibly three operating conditions. So, this would be the first operating condition, second and third, and what is the switch here? The value of the third terminal signal, in this case I am showing current, but it could also be voltage, will decide whether the device is going to operate at point 1, 2 or 3. So, that is how a transistor, which has a third terminal to control its response, can give you a switching effect. In the same manner, if I look at this signal, if I have a third terminal which has a value of I t, third terminal signal is I t. In the circuit, I am getting a signal which I will call I d. Then I am getting an amplification factor in this 3 terminal device of value I d over I t. Of course, when I say amplification, I need to make a device such that I d is going to be many times the value of I t, and that is possible to make in these devices. So, you see how a 3 terminal transistor device can be used either as an amplifier or as a switch, and these functions are very important for many electronic devices. And in order to know more about this, one can refer to some courses in the electrical engineering department. Now, we talk about more on the device aspect only. What kind of devices can I make which will give me transistor characteristics? So, there are 2 kind of solid state transistors, 2 basic kinds of solid state transistors. One is called BJT. This is bipolar junction transistor. And the other one that we will discuss is Mosfet, which from earlier lecture we have had discussion, metal oxide semiconductor, field effect transistor. By far, Mosfets are more commonly used compared to the BJTs. They have definite advantages over BJTs, but for the discussion in this course, let us discuss the main operating principles of both of these transistors. So, if I first let us talk about BJTs. The basic principle of a BJT is based on the PN diode. In our earlier lectures, we have seen that if I have a PN diode, the PN junction, where the material is P type here and N type here, and then if I connect it to a circuit and apply proper bias, I will get a behavior, a diode behavior, which this equation we have derived earlier. Now, this particular diode, if it is working in the reverse bias, at that point if I am going to apply, let us say take a simple example, if I shine light on it, then we know that this is a situation where this diode is being used like a solar cell or as a photodetector. And what happens in that case is, as we shine more light, we create more carriers in the depletion region of this PN diode, and the reverse current increases. In this manner, where this is the direction in which the intensity of light is increasing. So, if we now look at this curve, we will see that by just taking a PN junction and applying light to it, we have created a transistor. You may not see it in the same way that was drawn earlier, but if I reverse this, basically if I take the negative axis to the positive axis, this is basically a junction behavior. I have a device whose response can be changed by applying how much light intensity I shine on it. So, in this particular case, in this particular example, the light emission is my third terminal to that I need. But when I am making an electronic device, generally I am not going to use light as a third terminal. So, in order to then make an electronic device, what we do is we use another p-n junction to inject carriers in a reverse bias diode, and hence the bipolar junction transistor is a either NP-N combination. There are two p-n junctions here, NP and p-n, or p and p. So, in this particular case, let me first take the example of p and p here. The other one can be worked out in a similar manner to this discussion. So, what I am going to use here is I am going to have two junctions. The first junction is the p-n junction, this is p type, this is n type, and the second junction is very close to the first junction, which is NP junction. And so, I am going to now bias these junctions such that the first p-n junction is biased forward biased, and the second one is reverse biased. So, in this situation, if we look at what will happen in this device, we will find that if I am going to bias it and the bias would be such that it is forward biased, and for the second one the bias would be such that it is reverse biased, and I am going to have a current flowing through this one, which we call the emitter current, and this particular part is of the bipolar junction transistor is called emitter, and there will be a current which we call coming out from the middle portion, which we call base current, and this part is called the base, and then there is a current which is coming out from here, which we call collector current, and this part of the bipolar junction transistor is called the collector. Now, in this situation, the first junction, which is forward biased, is going to inject lot of holes in the base region. The base region is this, and the base region is taken such that these injected carriers then do not get enough time to recombine, and then they get into the depletion region of the second p-n junction and are and go through the circuit because of it being reverse bias. So, whatever current you are going to flow inject carriers you are going to inject in the first junction are basically taken up by the second junction and they flow through the device. So, in this particular bipolar junction, we get a behavior in which the third terminal is the base, and it is the base current which is the signal, and the behavior for the collector current versus the voltage for different base current is going to be of this kind, and here we have a transistor. So, using a single diode and using two diodes in combination, we get a bipolar junction transistor, where we use the base current as a third terminal to control the current of the device in this bipolar junction transistor. The important part in this particular discussion device is that whatever in the base, whatever current is or carriers are injected in the base, they must not recombine in the base. So, in this particular case, if the holes are injected in the base from this forward bias junction, most of them should continue and get collected by the collector in the outer circuit, and only a very small part goes to the base current. So, the total injected carriers are collected, and for that reason the device structure should be made correctly, so that we get a good transistor behavior. So, this is a bipolar junction transistor. We can have NPN also and get the transistor behavior from this particular device. Now, let us discuss the other important transistor, which is Mosfet. Now, for this discussion, we are going to base our discussion on the knowledge of the earlier lecture, where we discussed metal oxide semiconductor capacitor. So, we are going to see how we use that metal oxide semiconductor capacitor first to make a transistor. So, what did we do there? We had a semiconductor. Let us say in this particular case also I take a p type semiconductor. On top of that semiconductor, I have oxide, and I am making contact through the metal on top. So, on this is making the metal contact, and here I was applying a voltage. In case of capacitor, here the voltage applied we call the gate voltage with respect to a reference, which we will define little later. And the p type semiconductor is also contacted, where we apply the bias with respect to the device here and see what happens. So, just to review, what we did last time was that depending on what is my electronic structure is, what is the work function differences and other things are, and what is the applied value of Vg, I am going to have different states of carrier accumulation or depletion or inversion in this portion of the semiconductor, and that particular behavior I am going to use in a Mosfet device. So, let me make the structure of a Mosfet device around this particular MOS capacitor. So, this particular oxide is grown and then metal is contacted. Now, I need to make use this channel. So, I need to make contacts to that channel. So, I am going to make these two portions of my semiconductor N plus. In order to make these two portions, I must have had some amount of oxide here. This is for the mask portion, and this is also the oxide. I am making contacts to the gate metal. That is the contact to the gate metal, and I am going to make contacts through this N plus portions also to connect to the channel, and this I am going to call drain and source. Since this is a symmetric device, it does not matter which one I call drain and which one I call source. So, there is going to be I am going to call this the source, and I am going to ground it. There is going to be voltage applied here, which is V drain. So, here I have a device now. What I have done here is taken the MOS capacitor and built around it a structure to access the channel which is made by the MOS capacitor. So, now what I need in order for this device to conduct, if I am going to apply a voltage between source and drain, let us say Vg is not there, third terminal is not there. If I am going to apply a voltage between source and drain, these are N plus, this is P type, and there is going to be a diode created here, and one of these diodes, whether going from N to P or P to N, is one is going to be forward biased, the other one might be reverse biased, and in that case I am not going to have any current flowing through here. So, when there is no gate voltage, when there is no accumulation of charges, when no accumulation no inversion region, then even if I apply a source drain voltage, there is going to be no conduction through here. Then I apply Vg. When Vg is increased, first I will get a depletion region, and depletion is going to be created in this manner, because if I am applying a Vg, source is 0 and Vd is at some positive value. Let me take this to be a positive value, and hence there is less depletion, more depletion in the Vd side and less in the source side. So, there will be a depletion region. If I continue to increase Vg, when Vg is less than the threshold voltage, and if you recall, the threshold voltage in case of a MOS capacitor was the value at which the inversion sets in. This we have discussed earlier, at which point phi of S was equal to 2 phi of F for a MOS capacitor. So, when the when Vg is less than threshold, we only have depletion. When I have the value of Vg which increases from threshold, which means inversion layer starts, and then I am going to get a layer here which is going to have, in a p type semiconductor, electrons, and this layer is then going to connect the source to the drain, and I am going to have a current flowing through the device. ID will increase. So, let me summarize what I have just said. In this particular device, where we have a MOS capacitor in the center, if there is no voltage applied and there are no access carriers in the channel here, then when I am applying a drain voltage, there will be no current flowing, because this is a NP PN combination here. When I increase the gate voltage, then a current will flow, because basically by when I have a channel here, I am reducing the resistance here. Initially the resistance is too high. When the resistance is reduced, there is going to be a flow in the current, and I am going to increase the flow of current. So, if I show this behavior in a more simpler schematic, I can plot only the behavior of source and drain and enlarge it. So, let us say this is N plus the depletion region is in this manner, and the channel is created close to the interface with the gate. When I am going to apply a Vg, and here I have the source which is grounded normally, and the Vd which is positive. So, this is the situation in which I am looking at the whole behavior, and as I increase the Vg, the current is going to change. So, let us look at the ID. If I plot for this particular device for different values of Vg, the drain voltage, Vd refers to the drain voltage and the drain current, and the drain current is normally shown in this direction, positive ID, and in this direction ID here. So, if I am plotting ID Vd, when there is no voltage applied, what I am going to see is, I am going to see absolutely no ID, because the resistance is too high between the source and drain, and there is going to be no current flowing. When Vg is greater than V threshold for the MOS capacitor, then I am going to start seeing increase in the current, and as the Vg is increasing, then my charge accumulation here increases. So, I am going to see more charge accumulation when the Vg is increasing. So, there will be less resistance. So, this is Vg increasing in this direction. So, Vg is greater than V threshold, but and then it continues to grow and finally, it saturates out. So, what is happening at higher Vd? So, at a particular given Vg, if I am applying the drain voltage for this value, it works as a resistors, but at one particular point what we see is that the Vg becomes equal to the drain voltage here becomes equal to Vg minus V threshold. At this particular point, I have basically the voltage here, dropped here between the gate and the capacitor is 0. As a result, this particular channel is pinched off. So, if I plot only this particular portion, the channel at this value is going to look, the channel is getting pinched off right at the edge of the drain, and as a result now there is increase in resistance and the current gets reduced after this pinch off point, and then eventually it saturates out. So, if I plot for different Vg, same behavior occurs. When I increase the Vg, there is more carrier accumulation, resistance is less. Eventually again there will be a point where Vd will become equal to Vg minus V threshold. At that point again there is pinch off of the channel. This is known as pinch off of the channel, and beyond that point the ID saturates. This is called ID saturation, and one can plot the line for the pinch off for this behavior. So, you can see how a MOS capacitor is changed into a transistor. This is a behavior that we are looking for. We are looking for a transistor behavior in which the third terminal, in this case this is not the current, but the voltage is used to get a different ID Vd behavior for different values of Vg. Now, this particular Mosfet, what we just discussed, was made in p type semiconductor and the channel was n type, and hence we talked two different kind of Mosfet. One is called n Mosfet, which is a n channel. The channel which is created due to inversion is n type. The other one is p Mosfet, where the channel created it is a p channel. Further, there are more variations in these Mosfet. Each of them can be either created, the channels can be created by inversion as we discussed, and that is known as a depletion mode, or it can also be created in accumulation. This is the term that comes from the MOS capacitor when the majority carriers are getting accumulated near the semiconductor oxide interface, and this particular transistor is then called enhancement mode. So, it is clear that the similar behavior of the transistor can be obtained in different type of materials. You can obtain it by different mechanisms. Now, let us look at what if we can figure out how much is this value of the ID that I am going to get in a Mosfet. In order to try to analyze that, let us look at the channel itself, because if we continue our example, this is a n type n Mosfet, and the channel that we created, and I am going to enlarge the figures to explain things, is over here. I am making this as if it is same, but it is not going to be the same, because we apply a Vg here. This obviously is at this end, it is 0, the source is 0, and I am going to apply a VD source here, which means that at this particular point the voltage difference at this point is the gate bias minus the 0, but the voltage difference at this point is the gate bias minus the drain bias. So, the voltage is not the same as we go in this particular channel from source to drain. So, if I define this point as 0 for the channel and this point L. So, channel length for my MOSFET is L, and in that case the voltage applied here is more compared to here, and this is always going to be in this particular nature. So, now we want to calculate what kind of current, what would be the ID that will be flowing through this channel that has been created. So, the current that will flow through this channel is going to be equal to whatever is the charge here multiplied by the speed at which that charge is moving. So, if I take for this channel, then this channel also has a width. If I am going to plot the top view of the MOSFET, then basically the contact, the drain contact and the source contact, this is the drain, this is the source contact, and below we have the gate, and this is the width of the channel, and this is the length of the channel that we have enlarged over here. So, the current that I am trying to calculate between source and drain, the ID current, is going to be equal to, in this particular channel that has been created, how many charges are flowing per centimeter square per second from drain to the source. So, the charges that are flowing is going to be equal to the ID times the total amount of charge in the inversion layer, the n channel layer, and that, as I just mentioned, is going to be a function of y. So, I am going to call this direction as y and multiplied by, this is where q is the charge, inversion charge per unit area. So, any point y in the channel, it will be the charge per unit area multiplied by the width of the channel multiplied by the velocity at which the carriers are moving at point y, and that will depend on what is the voltage at different points. So, it is going to be a function of y, and that is why it comes into this equation. Now, if we analyze this further, we can find out what V of y is going to be. So, the velocity of carriers at particular point y, we can write that from our earlier discussion on drift. It will depend on the mobility multiplied by and it is an n channel. So, for electrons multiplied by the electric field at point y, and the charge for electron is negative. So, it is going to be in the negative direction, and electric field, if we take the assumption that the voltage between source and drain is V d, is going to be gradient of V at point y, and again a negative sign that takes it out. So, we have velocity of carriers at point y is going to be given by this. So, the total current ID that I want to figure out is going to be equal to q of n at point y multiplied by the width of the channel and mobility of electrons in the channel and the gradient of the voltage in the channel. Now, I need to estimate what this charge is going to be, and for that we will go back again to our MOS capacitor discussion. So, what is the charge in the channel? Charge in the channel is nothing but, due to inversion we can go back to our capacitance value for the oxide, C of ox, the gate voltage applied minus the threshold voltage minus the voltage at point y. So, this is the charge in the channel, and if I now put it back into ID, the current at any particular point ID total current has to be obtained by integrating it over the whole channel length, the total charge that is moving, mu of n W C aux integration for 0 to the drift voltage, drain voltage, minus V threshold minus V of y d of phi. Now, this is if one integrates this, one gets a expression for I of d. The drain current is given by, once the inversion sets in, it is given by C of aux divided by the channel length V g minus V threshold minus V d by 2 times V d. So, this is the expression for drain current as a function of V d and V g, and if we try to plot this expression, you can see how we will get the Mosfet behavior here. So, if I now try to plot V d versus I d, once again for different values of V g, and I am going to get curves which for a particular value of V g 1, second curve will be at a higher V g double prime, and if I go to even higher value, so this is for a higher V g double prime is greater than V g prime, V g even higher value is going to be even higher than this. Now, this looks does not look like a transistor, right? It does not, here initial behavior is, the initial linear behavior is correct, but beyond that it seems to be getting into a regime where you have actually a negative resistance and then coming down to a 0 current. Now, that is not what is expected, and the reason for that is the equation that we used apply only at the beginning of the inversion layer. At the point where we have discussed the pinch off takes place, that equation does not apply. So, at the pinch off point, when the applied drain voltage becomes equal to the V g minus V threshold. So, for each value of V g, it occurs at a different point. So, this would be the pinch off point for V g prime, pinch off point for V g double prime will be here, and for V g 3 prime is up there. So, the pinch off starts from here, and at pinch off, after that, when we continue to increase the gate voltage, the current does not increase. So, the and this equation does not apply for pinch off. So, at that point the current saturates, and that is why we see a behavior like this. And this is ID saturation. So, in order to get the value of ID saturation, if we replace V d is equal to V g minus V threshold, we can calculate the value of ID saturation, comes out to be equal to mu n C of x, and that comes by substituting this in equation, in the earlier equation, W divided by 2 of 2 by L V g minus V threshold square. So, you can see this behavior is right. The saturation value does not depend on the V d, it only depends on what gate voltage I am at, and that would decide my saturation value. Now, this may puzzle you, why does the pinch off occurs and why do things saturate? We have not explained that part so far. So, what all we said was that when I create the channel, at some value of the Vg that the channel gets pinched off at the drain. So, there is pinch off of the channel. If I am going to continue to increase the Vd, this pinch off is going to increase. So, this is going to move more in this direction with increasing Vd. So, why is it that the current is getting saturated at this point? Now, in order to understand that, it would seem like that a channel which had a low resistance, once it is getting pinched off, its resistance is increasing, but with increasing resistance one would expect, if the earlier equation was correct, that the current will go down, but that does not happen, because the reason for that is that whatever carriers are injected here, they once they start getting accelerated towards the drain, even if there is a pinch off, they are collected by the source here. So, in the pinch off region, the carrier acceleration or the velocities are so high that the pinch off does not affect the current due to pinch off, and this is why the saturation is because the ID is not affected by the pinch off, but there is no increase in the ID. There is also another explanation for this pinch off, where it says that at the point of pinch off, your V, the velocity of the carriers is already close to the saturation of the carrier velocity, and hence once we increase the Vd beyond the pinch off, the carrier velocities can't increase any further, and that is why the saturation takes place. So, this is the reason for pinch off and the saturation in the Mosfet transistors. Now, in terms of characterizing the transistor, if tomorrow I need to go and buy a Mosfet transistor, what kind of measurements or specifications I should have? There are the one thing that we discussed so far is what is called a output characteristics. Output characteristics are plotting the drain current versus the drain voltage for different values of Vd. This is for different values of increasing the gate voltage, and it is plotted between ID and Vd. There is another characterization that we use often in MOSFETs is transfer characteristics. And in this particular measurement, we are going to plot the drain current versus the gate voltage. And how does that curve look? That curve we can use the equations that we derived earlier for a particular values of for constant Vd, and we can take a Vd which is at in the linear region. This is a linear region of the MOSFET curve. This is the saturation region of the MOSFET curve. This is linear region. This is the saturation region, and we can plot the IDVG, and what we find is that this curve initially when Vg is very up to the threshold, there is no increase in the current. At the threshold value, the current will increase and saturate for a constant Vd, and this particular point is what we is the threshold for the MOSFET, and we also define a current called I off, and this is I on. So, we define a ratio of I on to I off. The slope of this particular transfer characteristics gives us the mobility of the semiconductor. Now, generally this mobility is not the same mobility that we have discussed in module 3. This one is called field effect mobility. And the reason why it is different from the earlier bulk mobility that we have discussed for semiconductors in general, because in this particular case we have the interface and the carriers are only, the electrons or holes are only moving in this particular channel. As a result, there is substantial amount of surface scattering. And hence, typically the field effect mobility of semiconductors, which is measured in Mosfet, is less than the bulk mobility of the semiconductor. And finally, there is this portion of the transfer characteristic, which is below the threshold, where there is some amount of current is seen, and that is known as a sub threshold region. And it one can think of this as a leakage current, and a small value of that is probably more desirable for most applications, and it relates to the defects at the interface and in the materials itself. So, this is also an important part of the characteristics of the Mosfet. And if we summarize our discussion so far, what we have covered is summary of this lecture. We have covered a very important device, transistor, how it is used as a switch or as an amplifier. Then we have looked at what different kind of electronic devices can be used as a transistor. We have looked at bipolar junction transistor, and we have looked at the functioning of a Mosfet and how to what are the characteristics of a Mosfet device that we can calculate, and also use those characteristics to understand about the materials interfaces as well. With this, I will like to close this lecture, and people who are further interested in understanding how the transistors are used in electronic circuits are requested to take up the lectures in the electrical courses in that area.